We've been writing all our vectors as columns, but that was sort of an arbitrary choice. We could have written all of our vectors as rows instead. And in fact, if you switch a column vector into a row vector, that is almost like a whole new operation on vectors. So what we could do is figure out if we have a linear vector function that works on column vectors, there should be a corresponding linear vector function that works on row vectors. What would the matrix of this row vector linear function actually look like? Well, let's figure that out. So here I have a linear vector function that works on column vectors. So it takes the column vector x1 through xn and multiplies it by this matrix, which is representing a linear vector function, and gives us this new column vector. So what we want to do is sort of translate this all into row vectors. So here's the row vector that corresponds to the column vector x1 to xn. It's just the row vector x1 to xn. And we should send it to the same output, except instead of writing it as a column, we should write it as a row. So this is a little non-standard because in this expression for our column vector output, this I is acting like a row index, which is the usual thing because it comes first. But when we switch to row vectors, this free index is indexing columns. So we kind of have to write things out explicitly to make that clear. So this is sum from k equals 1 to n of a sub 1 k xk, and then so on down to the sum from k equals 1 to n a sub m k xk. So this is the resulting row vector. So what we need to do is figure out what is the matrix of coefficients that represents this linear vector function. So if we call this vector just x, right? So this matrix is A, but the matrix that represents our row linear vector function probably isn't exactly the same matrix, so let's give it a different name. Let's call it B for now. We'll come up with notation for it later. X as a row vector, X is 1 row by n columns, and B, well, after we do this map, we're supposed to end up with a matrix that is 1 row by m columns. Is that right? Yes, m columns. We're supposed to end up with a no, x is 1 by m. I'm sorry. We're supposed to end up with a matrix that's 1 by m. But whatever the dimensions of this matrix B are, right, it would use up sort of the inside dimensions, and the resulting matrix product is not usually, unless n happens to be m, which isn't always the case, it's going to be impossible to choose a size for B that makes this matrix product give us a 1 by m vector as its output. So what this is telling us is this actually isn't the right matrix product if you're using row vectors instead of column vectors. If we want to multiply x by a matrix and end up with a row vector that's 1 by m as a result, we need the matrix on the right-hand side instead of on the left-hand side. And we need to use up this n because our target size doesn't have an n in it. So we need to use up that n, so we should have n rows. And we need to have m in our result, so we should have m right there. So with this matrix product, the n's are going to get used up, and we end up with a row vector that's 1 by m as a result. So one surprising thing about switching to row vectors is linear vector functions aren't multiplication on the left by a matrix, they're multiplication on the right by a matrix. So that sort of shows us why it's sort of awkward to have have these indices this way, it's because we're sort of using the indices backwards. So maybe what we should do is switch the indices, right? If we since the matrix product we know we need is x times a matrix, let's turn these around. So x sub k a 1k up to sum from k equals 1. I didn't write my sum. K equals 1 to n. Sum from k equals 1 to n. A x sub k a sub m k. Okay. And our idea is these are going to turn out to be the entries of a matrix, but you can see for these formulas to be describing a matrix product, this index is in the wrong place, right? Because the right hand factor in a matrix product, the index on the sum in the matrix product should end up in the first place, not in the second place. So what we should do is we need to rename all of these entries, right? What we should do is we need some entries for b so that it looks like b sub k1 up through sum from k equals 1 to n x sub k b sub k m. And so what this is telling us is that b sub, I guess we should call it ji, right, is if you compare the a's and the b's, right, the a's are what we have, the b's are what we want. So the b's have to be just the a's, but with the indices reversed. So b sub ji is a sub ij. Okay, so this gives us our new vector, our new matrix operation. If we have a matrix with some entries, aij, and this is m by n, when we do this matrix operation, what we get is the same entries, except the way they're arranged in columns and rows is switched. And this is n by m. So this operation is called the matrix transpose. So the way to write this is aij transpose, and there's a capital T is our symbol for transpose. And it's just AJI. So this just says that we switch rows and columns. And that translates a matrix that is a linear vector function for a column vector into the matrix that is the same linear vector function but for row vectors. All right, so if you actually write everything out rather than using this abbreviation notation like I've been doing, if you actually write them out, you can see across the first row, for example, you have A11 and then A12 and so on. Those actually switch, those were the first row, those become the first column of the transpose. So A12 down to A1n in the first column, and then the last row becomes the last column. So what was a row for the original, when you take the transpose, turns into a column. Of course, what was a column, here's the first column in A, turns into the first row of the transpose. So the matrix transpose just sort of switches rows and columns. Another way to think about it is it reflects the matrix entries across this diagonal, right? These two switch, right? Everything reflects across the matrix diagonal. Of course, entries on the matrix diagonal just sort of reflect to themselves, and that's why A11 hasn't moved here. Whether AMN moves when you take a transpose depends on if M is bigger than N or not. Okay, so let's actually work out an example of writing down a matrix transpose. I hesitate to call this a calculation because really, we aren't changing these numbers, we're just rearranging them. So the first row, 1, 2, 3, 4, becomes our first column, 1, 2, 3, 4. And then the second row becomes our second column, 5, 6, 7, 8. And then the last row becomes the last column, so 9, 0, 1, 2. And then just as a check, notice that the first column became our first row, and so on down to the last column, which became our last row. Also, notice that this matrix, the original matrix, was 3 by 4, and the transpose is 4 by 3. Right? So the dimensions of the transpose are just the opposite of the dimensions of the original matrix.